Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to talk a bit about Markov chains. Why I say processes? Chains. Okay, so this one's also going to be a skim. So I'm not going to focus too much on the topics of these, but this is one of those linear algebra combined with probability and stats, I think. I'm not sure, but we'll see. Right, so sequences of vectors arise naturally in certain applications. So in those considered here, each vector in the sequence is found by multiplying a special matrix times the preceding vector. And so to illustrate this idea, we begin by recalling the following scenario. Okay, so here we are going to go through an example, and I'm not going to type this. No way am I going to type this. Oh, I took a picture of myself. That's not good. Let me just take a screenshot of the problem. I'm not going to write all of that stuff. I'm going to start off in an example. And then here's a figure to go with that example. So for one, we're going to have to read these first before we even go into the problem itself. Because we need context, right? What's about context? So in a small town, there are 10,000 homes. When it comes to television viewing, the residents have three choices. They can subscribe to cable, pay for satellite service, or they don't watch TV. The town is sufficiently remote, so an antenna won't work. In any given year, 80% of the cable customers stick with cable, 10% switch to satellites, and 10 get totally disgusted and quit watching TV. And over the same period, 90% of satellite viewers continue with satellite service, 5% switch to cable, and 5% quit watching TV. Wait, let me look at this. So in any given year, 80% stick to cable. 80% of the 10,000 the cable customers. Okay. 10% switch to satellite, 10 are done. Over that same time period, 90% continue with the satellite, 5% switch to cable for the same time period. Oh, this one, what this sentence is saying is different from the other one. In a given year, 80 stick to cable, 10 switch to satellite, 10 is disgusted. Oh, no, it's a different idea. And over that same year, the time period, so over that same year, 90% continue with satellite, 5 switch to cable, and 5 quit watching TV. And of those people who start the year not watching, 85% continue not watching, 5% subscribe to cable, and 10% get satellite service. If the current distribution is 6,000 homes with cable, 2.5 with satellite service, and 1.5 with no TV, how many of each type will there be a year from now? How about 2 years from now, 3 years from now? So this is mostly prediction. And so these are, okay, so this is what it looks like. We have cable, satellite, no TV, right? 90% satellite, 80% cable, and 85% no TV. Then we have these switching. Okay, so let's start by forming the matrix. So when we think of them as vectors, columns of vectors, this vector here, what does that represent? The first vector represents this sentence. In a given year, 80% of cable customers stick to cable and switch and then quit. Percent, right? Now, in the second one, it says that 5% switch to cable, 5 quit TV. So we say this. And then this is 90%. 90% continue with satellite. And then of those people who start the year not watching TV, 85 did not watch TV. So we say this is 0.85. And then what else did we look at here? We say that 5% subscribe to cable, and then 10% get satellite service. Okay. So really, again, we're doing this idea of storing information in a compact way using matrices. So we start off with that. Okay. Now let's look at some buzzwords here, which I don't think you've seen before. I haven't seen this before. We're going to talk about stochastic matrix and doubly stochastic matrix. This is not super important. It's not part of the curriculum. I guess our teacher just wanted to put this out there, maybe because it's important to know. So we say a square matrix like A that has non-negative entries and columns that each add to 1. So actually all of these columns add up to 1. Okay, this is a 9. It's called a stochastic matrix. So a stochastic matrix is that that's a square matrix, right? Columns add up to 1. What else can we say? Non-negative entries. Those are 3 things. So this thing here that we have is a stochastic matrix. What in the world is a doubly one? Oh, it's really simple. It's also a stochastic matrix, but the additional feature, so this is a stochastic matrix with rows adding up to 1. So if we check this, 90, okay, actually this one is not a doubly stochastic matrix. Yeah, this gives me a 90. Oh wait, no, this gives me 100. 0 0.9, 0 0.1, 0 0.1. That one doesn't. 0 0.05, 0 0.10. This one gives me a 90%. So it doesn't add up to 1. Okay. And so previously we formed the vector x, giving the initial number of homes with each of satellite cable and no television. Wait, where did we form a vector x? Where did we do that? Huh. Or we're gonna do it now. This time we start with the vector. No, we didn't do that. Or we probably did before. We start with a vector that gives the initial proportion of homes of each type. Okay, so we're gonna start off with, so here we start with vector, let's just say x naught or x. Oh no, x naught. And this vector gives proportion. So we're talking about percentages here of homes of each type. And so how would that look like? So that vector is going to be 0.6, 0.25, and 0.15. Now, what do these all mean? To contextualize, 60% of homes have cable, 25% of homes have satellite, okay? And 15% of homes don't have television, have no TV. Okay? You might be asking, where in the world did I get that? Yeah, me too. Where in the world did we get that? These don't add up to 100. Oh shoot, wait, did they add up to 100? I don't think so. I I could try 3, 4. Oh shoot, they do add up to 100. Oh, wait, where did they add that? I actually don't know. So it's either cable, satellite. Oh, okay, so it did not mention. So this is a completely new information that someone just gave out of the blue. So x naught is the initial state vector. Each entry in x naught can be thought of as representing the probability that a household falls into one of the television watching groups. In general, any vector that has non-negative entries that add up to 1, so that vector adds up to 1, is called a probability vector. Thus, a stochastic matrix consists of columns that are probability vectors. Okay, so okay, lots of terms here, and they are quite scary. Okay, let's just go through it. So I'll go through it really fast. This is called the initial state vector, right? Because each entry in X naught can be thought of as representing the probability that a household falls into one of the television watching groups. Now, in general, we have this idea called the probability vector. And this is just non-negative entries that add up to 1. So this is for a vector. And so this is a probability vector. Then we also have, so yes, when we have a stochastic matrix, it consists of columns that are probability vectors. Okay, here, let me look at a nice one. So after 1 year passed, the distribution of household changes. So the new distribution is given by x sub 1, a x naught. So here we apply some linear transformation, or we transform this vector by multiplying it with a matrix A. So actually, we use the probabilities that we got last time. And we apply it here. And this is a nice way again, because again, we're just storing information. But this is really nice when we want to do everything in one go, kind of. Okay, keep going. Now here I apply it to this, the proportion of the homes. So that one was the initial distribution, and then applying it to here, we would get something. We'd actually get a vector out of it, and we'll call it x sub 1. So applying the information that we got from the problem now changes the probability of the households, right? So now it's 50% of homes have cable, 25 have satellite, 15 have no TV. Or no, 20, 30 have satellite, and 20 have no TV. So what is this? We call that a transition matrix. Because it is used to make the transition from one state vector to the next state vector. And so that is after 1 year, 50% have cable, 30 have satellite, 20 have no television. And then 2 or 3 years later, if we keep applying it, actually we can check. So as we keep applying this A matrix, we're gonna have, actually, I'll just take a screenshot of what it looks like 2, 3 years later. And then we can kind of analyze what this looks like. So after 2 years, 2 to 3 years later, well, now we have this, where x sub 2 has these probabilities, x sub 3 has these probabilities. So we can see that the probability of homes having a cable is actually decreasing, while the number or the probability of, say, homes having a satellite is increasing, as well as homes having no TV is also increasing from 15% to 20% to 23.5% to 26%. And so, okay, let's just do in general, but after a couple of years, and I think this one's really cool, we can actually assess the probability. We can look at, you can see what the probability of each is looking like. So this is our way of predicting what's the probability of each thing happening numerically. And so we see that after 40 years, 20% will have cable, 50% will have satellite, and 30% of homes will have no TV by 40 years. But that's a predicted value. And so this thing here is what we call a Markov chain, right? So given, so this one is, so given a sequence of vectors, and so we say x naught, x sub 1, all the way to something, is the Markov chain. So that was the concept that we were trying to get out of the way. And so examining the state vectors all the way to that 40, we see that our sequence appears to be converging toward the vector. So examining state vectors from x naught all the way to x sub 40, they appear, but we're not sure, right? They just appear, so based off of intuition, to be converging to this vector here. 0.2, 0.5, 0.3. And we can just use a computer to run this out. But informally, by converging, we mean that the entries in the sequence of vectors are getting closer and closer to fixed values. Okay. And so what do we call this idea? We call this a steady state vector. It's also a state vector, but it's steady. if we were to apply it to some A, the original vector X. Okay? So we would call that the steady state vector. And so there are some other interesting things that we can do with this here. And there are some proofs. I'm not going to go through that. Oof. Hmm. Hmm. Now let's try to, okay, maybe this is going to take just a bit longer. I was expecting it to be done like right now, but I guess it's not. But there is a way to directly find this idea of steady state vectors. So I just think this topic is really cool. So finding steady state vectors. So we have a systematic way of doing it. So we say that again, we start off with this initial state vector, we apply some matrix A, we output this steady state vector, and then we say that this thing is just equal to the identity multiplied by that steady state vector. So when we subtract these, we get a zero vector. And so we can then say, or we factor out this A minus I. We factor out the X, you would still get that zero vector. And so thus a steady state vector for A will satisfy the homogeneous system with coefficient matrix A by I. So let me explain how to do it. So say we have this example, A is I, and we have this matrix negative 0.08, 0.08, 0.40, negative 0.40. Now that thing right there, and so the homogeneous linear system, A minus IX equals 0, should have an augmented matrix, right? So our augmented matrix should be the following. And then we can convert this. So we can say this is, the nice thing about this is we can just add the two rows together and put them in one row. And so now we say this is an echelon form. And so that leaves us with a single equation, right? So we have this equation here. This thing is equal to 0. And we set x sub 2 to be s, because that's a free variable. And then substituting, we get this general solution that x is just s multiplied to 5 and 1. Okay. Now, since x is to be a probability vector, the entries need to add to 1. So we need the entries to add to 1. How do we do that? Wait a minute. How do we get 2 here? That's funny. We just need this. We have s. Wait, let me actually try and solve this myself. So this would be equal to 0.08 x sub 1 is equal to 0.4 s. And so when we try to solve for x sub 1, we would get 0.4 s divided by 0.08, which, okay, maybe that might be a number for x sub 1, but I'm not super sure. Oh, it is a 5. So we actually have a 5s here. Then since x sub, okay, then that's just a 1 because that's the coefficient. Okay, okay, this makes sense. So we basically need entries to add to 1. And so what we do, so we set s to be what? 1 over 6. Huh, okay. Okay, so we say 1 over 6, 5, 5 and 1. That's going to be 5 over 6, 1 over 6. Because when we add these two, we get 6 over 6, which is 1, which is the steady state vector found in example 2. So now we have a steady state vector. Okay, cool. This idea of finding steady state vectors, even though the probability is also really cool. Okay, we have some examples here, but the idea again is just to convert it to augmented matrix. And we set the constants to be 0. We get it to row echelon form. We get the solutions. And we set our S to be something that makes sure that the components of the vector add up to 1. Okay? Right. So now we're going to look at properties of, actually, no, we're close. Let's look at properties of stochastic matrices. So what again are stochastic matrices? Stochastic matrices have column vectors, right? And their components add up to 1. And it's also a square matrix and non-negative entries. The probability can't be negative, I think. I'm not sure. I haven't really learned about, I don't have any stats knowledge. I do have a bit, but not as much. Okay, let's look at properties of stochastic matrices. So this next theorem is going to summarize some properties of stochastic matrices. And goodness me, I'm so happy we're not doing proofs here. Okay, we're at theorem 3.9. So here we're going to let A be an n by n stochastic matrix. And we also let x naught be a probability vector. So that means all of its entries add up to 1. I'm assuming that's also in Rn. Then what can we say about it? Well, property A is that if xi plus 1 is equal to an application of A to the initial x, right? And this goes for all I equal to 0, 1, 2, and we just keep going. Then each x sub I, x sub 2, all the way to something in Markov chain is a probability vector, which is interesting, right? So all of these vectors are going to have probabilities and they're going to total up to 1. And we did see that, right, in one of the examples. Let's not B. If B is another, say, n by n stochastic matrix, then we say the product AB is also an n by n stochastic. Now this one is a nice proof, I think. You guys can try it out. I'm not gonna try it. For each of I being equal to, so starting at 2, all the way to something, that AI, so all powers of A, is an n by n stochastic matrix. Okay, so those are the properties. And so the examples considered thus far, we could always find a steady state vector given an initial state vector. However, not all stochastic matrices have a steady state vector for each initial state vector. Okay. So there are some examples where it won't reach a steady state vector. Mhm. And so sometimes you have to pick a nice initial state vector in order to get a steady state vector. Oh, so a stochastic matrix may have many different steady state vectors. Huh. But yes, we want to go to a general solution. So just like what we've been doing, the fundamentals, right? In order to get to this steady state vector thing. Okay. Holy smokes. Okay, we have another definition and another theorem, and then we should be good. Okay, let's look at a definition here of one of these guys. So we look at irregular matrix. And so here we let A be stochastic matrix. I wish there was a nice math way to write this, so I don't have to keep writing stochastic. Then we say A is what we like to call regular. Why is it regular? If for some, it's talking about an integer, so it can't be a decimal. Some integer k greater than or equal to 1. So we're talking about 2. Then we say matrix. Now I misspelled matrix. Matrix A to the k. Oh, has all positive entries. So it's not going to have a 0 entry. I'm surprised. So it's going to be a positive. So it's going to have all positive entries, no zeros. Okay. Okay, we have one last theorem that we can go through, then we're pretty much done. We're going to let A be a regular stochastic matrix. So what does it mean again to be a regular stochastic matrix? Regular meaning all the entries of A are positive. They're not zero, they're all positive. What does it mean for A to be stochastic? All of the column vectors add up to 1. And A is also a square matrix, which we've also defined. We know what a square matrix is, right? So A is a regular stochastic matrix. Then, so for any initial state, so for any, I'll just describe it in English. So we have this initial state vector, we'll call it x naught. The Markov chain that goes all the way to something, if it's converging to a value, this x naught, x1, x2, keep going. Eventually, it's going to converge to steady state. We'll call that x. Okay. Now, here, let's talk about another thing. The sequence A naught, no, not A naught, A, just say A squared, A cubed. And if we continue from there, converges to matrix, it converges to some matrix X. And it actually continues where X is that steady state vector. It's a unique, so it's the only steady state vector. And this was actually given in part A. Great. Hope you guys enjoyed this video. I think this was an interesting topic, given that we looked at the intersection of probability as well as linear algebra. And so in the next video, I'm going to be going over exercises on both LU decomposition or factorization and Markov chains. So I hope you guys enjoyed. Stay tuned for that, and I'll see you in the next video.